All right, guys. This is the first lesson of chapter 5, and we are introducing probability distributions. So last chapter we were doing probability in all the operations, multiplication of probabilities, addition of probabilities, conditional probabilities, and now we're going to take it an extra step and we're going to talk about distributions. We're going to introduce discrete and continuous distributions, but we're going to focus on discrete random variables in this chapter. So again, the goal is to be able to verify that a particular distribution is valid, calculate some probabilities, and then classify a random variable as discrete or continuous. So those are the goals. So let's introduce the concept of variable. So a variable is defined as something that can assume multiple values. So here we have different values. All right, we're going to contrast that with a random variable. So a random variable can also take on multiple values, but the values are determined strictly by chance. So for example, when we're talking about outcomes for a die roll, if we say x is the random variable, then x can take on multiple values from 1 to 6, but the value that you get for x is strictly based off of chance, because you can take on any of these values and the probability of getting any value on a die is 1 over 6. So therefore each of them have the same chance of happening, but they're still based off of chance. So that's why it's a random variable. Variables in general can be classified as discrete or continuous. So discrete variables are basically countable variables, so they can take on values that can be counted. So the values here can be counted, so you can have either an infinite number of values that can be counted, or you can have a finite number of possible values. So for instance, with the die roll, you can take on 1 through 6, and those are countable values. They're whole numbers, so in general these are whole numbers. And you have a finite number of possible values. So in the case of a die roll, that's going to be something that is discrete. Another example is, let's say we're talking about the number of phone calls. Well, this is something that can be counted, right? You can't have -1 phone calls, but you can have 0 phone calls, you can have 1, 2, any number of phone calls, as long as it's a whole number and can be counted. So therefore, the number of phone calls can be counted, and therefore is considered a discrete variable. Continuous variables, on the other hand, can take on any value, so they can include fraction or decimal values. Okay, so these can include decimal values, and they can assume any value, all values in an interval between two numbers. So an interval. So for example, if you're doing like weight or temperature, those are things that can be interpreted in terms of decimal values. So those are also quantities that can be measured. So anything that can be measured generally can be put in terms of decimals, and therefore are continuous. So for example, with temperature, you can have decimals such as 92.3 degrees. With weight, you can have 105.6 pounds. So you can take on any kind of value, and therefore we consider that continuous. So number 1 is asking you whether the quantity is discrete or continuous. So the shoe size of a randomly selected customer. So shoe size, tends to be discrete values. So yes, you can have, like, say 1, or you can have 1.5, right? You can have 2, you can have 3, 3.5. Any of those shoe sizes are valid, but they're finite number of values, right? So there's not an infinite number of values here. And generally, even though this is not a whole number, it's still a finite value in the sense that you can't really have 1.25. You can only have a shoe size of 1 or 1.5. So even though you have a fraction here, this can still be considered a discrete quantity. Okay, so with the weight of patients in a hospital, we already talked about that earlier. That's considered continuous. because like you said, we can have 105 pounds, we can have 106 pounds, but we can have any number between 105 and 106, so 105.2 pounds. So that's considered continuous. The pump price of a gallon of gasoline, so you can have $1 or $3 per gallon. You can have $4 per gallon, or you can have any number between those, right? $3.21 per gallon. So that will be considered continuous. All right, the number of items purchased at a grocery store. Again, number of items, that's considered to be a discrete quantity. You can have 1 or 2 items or 10 items in a grocery store. So in this case, this is discrete, since it can be counted. All right, so now we're going to introduce a concept of a probability distribution. So a probability distribution is basically like a collection of values. However, these values are based off of chance. So the values are based off of outcomes, and the outcomes will happen based off of chance. So you're going to have each outcome, and usually the outcomes are in terms of values, with its probability of occurrence. So for example, in a die roll, your outcomes are 1 through 6, and that's a collection of values, and with each outcome or number on the die, there is a certain probability of occurrence, and that's known as a probability distribution. So now there are 2 requirements for this to happen. So in order to have a probability distribution that is valid, you have to have 2 things happening. All right, so the probabilities have to add up to 1 always for all events or all outcomes. All right, remember this little sigma here? That means that stands for sum, so you're adding up the probabilities. All right, and then this is your random variable. So that is your random variable. We usually use capital X for that. So, and then this P is probability, so the sum of the probabilities have to be 1. The probability of each event has to be between 0 and 1. Remember, the probability being 0 means that there is no chance of happening. So no chance to happen. And probability of 1 is 100% chance of happening. So 100% likelihood. All right. So now this is going to be, the probability is between 0 and 1. So you can have any decimal between 0 and 1, or you can have 0 and 1 inclusive. All right, so now this number 3 wants us to determine whether it's valid. So we're going to use the 2 rules here. So in this example, we are going to see if the probabilities are between 0 and 1. So it looks like they are between 0 and 1. So it satisfies condition 2. What about condition 1? So you're going to add up the probabilities here. So if you add up 0.2 plus 0.6 plus 0.1 plus 0.3, that's going to be 0.8, 0.9, you're going to get 1.2, which is not equal to 1. So this is not a probability distribution, so not valid. All right. For B, if you were to add up the probabilities here, notice that they are between 0 and 1. Now let's go ahead and try to add them. So we got 1/4 is the same thing as 2/8. We have 1/8, 3/8, 1/8, and 1/8. So we're going to add these together. Remember, common denominator is 8. 2 plus 1 is 3, plus 3 is 6, plus 1 is 7, plus 1 is 8. 8 over 8 is 1, so this checks out. So therefore, this is valid. So this is a valid probability distribution. Part C, again, if you add these up, you're going to get 1. And they are between 0 and 1, so this checks out. This is valid. Here, notice that it does not add up to 1. All right, adds up to 0.5, but also the probability is not between 0 and 1. Like, look at this one. That's problematic, right? So that is not between 0 and 1. All right, so not valid. All right, so now the next thing we want to look at is how we represent probability distributions. So this is how we represent them. So in order to represent them, we can use the table which is what we have here. So these are some examples of how it looks like with a table. You usually have your random variable on top and then your probability on the bottom, but you can also do it vertical instead of horizontal. So it can be represented with a table, just like above, and it can also be represented with a graph. Sometimes we can also represent it with equations, like functions. Alright, so we are going to show how we're going to learn how to construct it, a probability distribution with a table and or a graph. So the next example wants us to represent the probability distribution for the sample for tossing 3 coins using both methods. So in this case, x is the number of heads obtained. Alright, so now we are tossing 3 coins here. So we got to look at all the possibilities, right? So you can have all of them. So let's go ahead and list out. Let me list out our sample space here. Alright. List out our sample space. Remember, our sample space is our set of total possibilities, set of all total outcomes. So we can have all heads, heads, 1 tail, heads, tails, and heads, tails, heads, heads. Alright, that's it for 1 tails. Now we're going to do with 2 tails. So heads, tails, 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 heads, tail, 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 heads. And I think that's it for the tail possibilities. And then the last possibility is having all tails. Alright, so there are a total of 8 possibilities. Alright, so this is our sample space. So there are 8 outcomes. Alright, so therefore when we do our distribution, we are going to do, so we have x, this is part A. We have probability of x. Alright, so now we can have 0 heads, we can have 1, 2, or 3. So what's the probability of getting 0? Well, that would mean that you get all tails, which is this guy, right? So that's going to be 1 out of 8. Probability of getting 1 heads, so that would be 1, 2, and 3. That would be 3 out of 8. What about 2 heads? That would be 1, 2, 3 again. So 3 out of 8. And then the probability of getting all 3 heads, that would just be 1 out of 8. So notice this is a probability distribution because the sum of the probabilities is equal to 1. 3, 6, 7, 8. So that equals 1. So this is a probability distribution, is valid. So now part B, we are going to do a histogram. So we are going to do an x and a y axis. So this right here is going to be our probability, P of x. This is going to be the number of heads. Alright, so we can have 0, we can have 1, 2, and 3. Alright, so we have 1 out of 8, so we're going to do 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be 1 out of 8. Then 3 out of 8 over here, 5 out of 8, 7 out of 8. Okay, and then the last one is 8 out of 8. Alright, so then we have 0 is going to be 1 out of 8 chance. Alright, we have 1 heads is going to be 3 out of 8 chance. So 2 is going to also be a 3 out of 8 chance. And then 3 is going to be 1 out of 8 chance. Here I'm going to try to make this a little nicer. Try to spread it out a little more. And then this last one is going to be 1 out of 8. Alright, so that's our histogram, and that's our probability distribution. Pretty straightforward, and this is actually a symmetric distribution, so this distribution is actually symmetric. Alright, so now last example. Okay, so it says the Baseball World Series is played by the winner of the National League and that of the American League. The first team to win 4 games wins the World Series. In other words, the series will consist of 4 to 7 games, depending on the individual victories. The data shown consists of 40 World Series events. The number of games played in each series is represented by the variable x. Find the probability P of x for each x. Construct the probability distribution and draw a graph. Alright, so here they just give us the data and they want us to do the probability. So we're going to go ahead and include another column, if you will, and we'll call that P of x. Alright, so this will be our probability distribution here. So in this case, for x is equal to 4, right, we have 4 out of 8, or 4 out of 8. It's going to be, they say the total is 40, so it's going to be for x is equal to 4, there's 8 series played out of 40. So this will be 8 out of 40. Alright, and we are going to reduce that. That reduces to 1/5. Alright, so we got the probability of that is 1/5. Let me erase that. Alright, 1/5. And then for this guy, it's going to be 7 out of 40. So we'll put that in here. This guy's going to be 9 out of 40. And then the last guy is going to be 16 out of 40. But 16 out of 40, that reduces. We can divide that by 4, and that'll be 4 out of 10. And then we can divide that even more. We can divide that by 2, and that'll be 2/5. Alright, and that'll be for this guy. Alright, so that's the probability distribution there. And we're going to draw a graph. So okay, so in this case, that random variable x stands for the number of games played in each series. Okay, so number of games played in each series. Alright, so we have 4 games, or 5, or 6, or 8. Or I'm sorry, or 7. I don't know where I got 8. So that should be 7. Alright, and then we have our P of x, our probability. And we're going to do all this in terms of, you could do it in terms of 40 or whatever you want. So here what I'm going to do is I'm going to kind of convert these into decimals. Alright, so we're going to go ahead and divide this on the calculator, but you don't have to convert it into a decimal if you don't want to. So 1 out of 5 is the same thing as 0.20. 7 out of 40 is 0.175. 9 out of 40, 0.225. And then 2 out of 5 is 0.40, or 0.400. Alright, so in this example, I can kind of break these up into maybe like, you can break it up however you want, but it looks like we can probably get away with breaking it up by maybe like ones or something like that. So like 0.1 or something, maybe 0.15. So I'll try doing it like that. So 0.05, 0.1. So we're basically going by 50s if you think about it. So that's 150. And you could do it however way you'd like to. This is just one way that I'm doing it. As long as you're scaling by the same amount each time, it doesn't really matter. So in this case, you have 0.200 here at 4. we have at 5, x equals 5, we have 0.175, so it's between 0.15 and 0.200. Okay, for 6, it's 0.225, so between 2 and 250, so halfway. Alright, and then last one is 7, which is 0.4. Alright, and there's my probability distribution.